Awesome. Thank you very much. And especially thank you very much for the organizers for this invitation. It's good to see so many people still here. Yeah. Okay. Half of you are like asleep already, but the conference is nearly over. Okay. You have to survive my talk and a few more, and then everything is over. But I think you're at the right workshop here. And now we're doing a little bit of autonomous driving research. I think following up after Keshiv's talk with the title Overcoming Blind Spots, Occlusion Consideration for Improved Autonomous Driving Safety. So normally I ask in the workshops or in my lectures, if somebody came with an autonomous car. I know the answer already that not so many people came with an autonomous car here today. And one of the several reasons is that we can't to figure out how to drive exactly in these environments, right? I always bring this picture here in my lectures because it really demonstrates what are the difficulties, right? The environment looks very difficult. The environment is very difficult. And if I would ask you, where's the actual path that you need to follow in order to survive this environment, I probably would get 10 different answers. Yeah. So you see, even for humans, that's very, very difficult to navigate exactly in these kind of environments. So why is that like that? First of all, when it comes to autonomous driving, the first thing is adaptability. We haven't figured out, even with this novel research in VLAs, which we just heard, to bring that onto machine, and the machine adapts over time to different environments. Number two, the complexity. That's what we will discuss today. What is actually kind of funny when you see autonomous cars driving, they drive in Germany on highways, they drive in the US, and a little bit in China. That's it. So, but a few people here are probably like from South America. I don't know if you've been to Colombia, for example, right? When people cross the street in Colombia, they honk in order to indicate what they're doing next. Yeah, we have to solve that also for autonomous driving. And number three is definitely generalization. How can we actually generalize? So a big topic, if you look into all these three fields, is of course motion prediction. Yeah. Motion prediction is combined with uncertainty. We don't know actually what happens in the future. We can only guess. And the normal motion prediction research, is that a car drives on the street and detects what others are doing. Like here in this example, right? We want to predict what is the person doing. Let's see. All right. No, nobody predicted that one, but that is classical motion prediction. Okay, that's what we normally do. That's what we normally solve. That's why we have all these data sets, and that's where we develop the algorithms for. We did a little bit something different. Of course, we do also similar stuff as the others, but we did something different and looked into a special prediction part, which we call predict the unpredictable. And that is coming, especially when we talk about occlusions. So look at the left side. You see the truck. You see kids running behind this truck and behind this bus, and the truck has to brake. Of course, this is not only prediction, it also means you need to react to the kind of prediction. And that's also a special part of my research, like I'm a motion planning and controls guy. And so these occlusions, they happen all the time. And this is something I think we need to solve in order to bring autonomous driving into the real world. So, of course, I'm not the first one. People looked into that kind of topic a lot. We're talking about risk assessment for different drivers. We talk about visibility. What can I actually see? How far can my sensor look? This is a big part. And then, of course, the prediction itself. And we could start with a Kalman filter and say, let's predict what we have seen and then look into that. We can use deep learning architectures. I mean, there's so many algorithms out there. But then we talk about things we can't see. So this is then the field of POMDBs, partially observable. Or we do some formal research with, for example, reachable set estimation. So whatever we saw in that kind of field when we want to have it for the occlusions, we saw, number one, it's not scalable because we want to bring it into the real-world environment. Number two, it's not real-time processing. So if you don't know me, I'm a guy who likes to put the algorithms into real hardware and into real systems. So if it's not deployable, then it's not of interest for me. So I'm not a benchmark guy. I want to see that in the real world. And then number 3, and that's the most important part, how can I combine multiple traffic participants at the same time? Because people that walk are different from people on a motorcycle, are different from people on a bicycle, and are different from a car, but they all can be part of an occlusion. So that was the research question we tried to figure out. And we said, okay, let's go for something that is open source, can be used by anybody, and is like combining the motion planning and the motion prediction part. So today I present you this kind of solution. What we provided is basically an motion planning occlusion framework. So in this motion planning and occlusion framework, we first of all have, of course, the motion planner. So this is something fundamentally that you need in the beginning. Without that, it doesn't work. And then on the right side, you see the occlusion. And I want to walk you through this picture here, step by step together, that you get a good idea what is this all about. Let's start on the left side and start with a motion planner. In our case, we need a motion planner that generates trajectories. We are driving in real-world street environment, so for us, the first idea was, of course, going for something that plans in the Fresnel space. Why? Because you can sample efficiently trajectories longitudinally and laterally, and you can get them jerk optimal. So that's good for us. So what we are doing basically, we are looking into the scenario, we are initializing the planner, and then we are starting to sample the trajectories. And it looks like this on the right side. So what we did in order to make this fast as possible, number 1, change the code architecture. This thing is running in C++. Number 2, having a heavily tuned cost function. And number 3, optimizing the sampling itself. So we are not random sampling, or we are not random sampling into the future. We also do not have a fixed sampling path. We optimize for the movement of the vehicle. And therefore, we are able to sample 800 trajectories in 8 milliseconds. And this is quite fast because 800 times you get a decision in front of the car and then you can select the one you need. So this is basically the fundament. And with this kind of fundament, because we know we have these trajectories now, we can go into the next step. Because now comes the important part for this talk, it's the occlusions itself. How do we calculate that? So the first thing we do is that we take all the objects that are around us, we take the object detection, and then what we do, we create the occlusions, geometric occlusions behind these objects. So for example, you see here a car on the left side, and when we drive in front of that car, there is a potential occlusion, a potential geometric space behind that. So we know that. So what we do now, in this geometric space, we create so-called phantom objects. Why phantom? Because they might be there or they might not be there. It's like Schrödinger's object, okay? It's there or not. We don't know. But what we do, we say there is something. And now comes the second important part. Based on the size of the object, based on how large this object is, there might be different phantom objects behind that. So imagine behind me, there can't be a truck behind me, but there can be a child behind me, right? And behind a truck, there can be anything because it has such a large occlusion space. So we place these kind of phantom objects inside, then we predict them. And with that kind of prediction, we then calculate certain metrics like time to collision or displacement errors, the behavioral, and then we do a safety rating, and then we decide what are we doing with our motion planner. So we are closing here the loop, and that's what I meant in the beginning. The motion planner, the motion prediction, the occlusion behavior is now coupled all together and is running in a constant loop. So that is basically the magic behind that. Let's have a short look into the prediction algorithm because it's the workshop for prediction, right? We want to see and hear something about that. So what we basically did, we have a heavily agentic-centric grid-based approach. So we have a decoder-encoder architecture, and in this one we are combining the attention-based encoders with a convolutional decoder. So we are running here, of course, on a data-based algorithm because we not only see in the benchmark that this is the most best one or the most prominent one, we see also quite efficiency improvements. in total, we have 1.2 million trainable parameters, and we have a runtime of roughly 42 milliseconds for 128 pedestrians at the same time. So we can speed this up quite heavily. So why does this work so good for the occlusion prediction? What we are doing, we are basically trying to get the map information, trying to get all the objects, and then what we are doing, we are vectorizing this map encoding. So what we are trying to do based on the focus area, the occlusion, again here, this is why we are doing that. We are trying, and now look closely, to take the information from the map and input or take the lane boundaries alongside the semantics compared to the pixels and put that into the map tensor. At the same time, what we are then doing, we are trying to figure out what all the objects are. Remember the phantom objects, and have a so-called social tensor. So I'm just switching back here. You see these objects coming from the occlusion and then moving into the map tensor. And this, in combination and with the architecture, especially cross-attention, we have the possibility to model these kind of interactions. Number two, we have the possibility to reduce the parameters by factor 10. So this is where we can speed it up, and therefore also then an improvement of the runtime. So you see, it's three components. It's number one, the motion planner. Number two, the whole architecture of the occlusion, like the concept. And then number three, the motion prediction itself. For the motion prediction, we are then actually, I think we have a reasonable accuracy, especially for detection of 2 time steps or 10 time steps. You have an improved estimation of speed and heading, and especially in comparison to other algorithms, I think we have a competitive performance. We are not outperforming somebody here, I have to admit that. And remember, it needs to work in combination with the whole architecture. Otherwise, there is no fun in it for us. So look at just a few examples where we predict the trajectories. You see here the ground truth trajectory. You see, the prediction trajectory in green is the 2-second prediction. The yellow one is the 10-second prediction. I mean, you see, of course, not only from the data sets, but also here from some qualitative examples that the prediction here, it's for pedestrians, is actually quite good. And to show you a final image from our real-world car, this is basically the car in a bird's eye view. You see multiple objects around it in blue. And then, of course, behind that, this is the occluded traffic participants. You see here the prediction working out. So in summary here for the methodology, the key takeaway is that it's the three-folded motion planner, concept, and the final prediction coming all together, then allowing for us to do this occlusion-based detection and therefore hopefully achieve a better result than before. So now, finally, let's have a look into the results where I brought you with some examples where you can see if that concept actually works out or not. Unfortunately, I can only bring you some simulation examples today because we haven't tried it yet in a real-world car scenario because we need a test environment for that. But I think the simulation results give you quite a good idea. Bless you. So let's look at the results. What you see here are two examples. One scenario, two examples. If the example is in red, the occlusion failed. That means we were not running with this occlusion-based planner. And in green, you see the same scenario, but now solved with our occlusion-aware motion planner. What you see is that the truck is passing by. Behind the truck, there's theoretically a bicycle that misses us. And what you see in the top video is that we would crash this bicyclist. Of course, because we are not occlusion aware. In the second one, you see, based on the metrics we have chosen, based on this risk matrix that you see on the left side, that we would avoid this bicycle. And you see that we are slowing down the car and even moving a little bit to the right side. So our car can actually react now to these objects based on the prediction, and remember, based on the phantom object we placed here. So we enabled that the scenario can now be completed without an accident. What you also see on the left side, that this is not a solution that you get by just combining these algorithms and throw them at it and say, oh, now everything works. We played, of course, heavily with a parameter set. And you see also when our risk metrics in total are too high, even our car would crash with the based or in this occlusion-aware scenario. Let's have another view. This is a left turn intersection with a truck. Now let's have a look at the left turn intersection with a car. Same scenario, same setup, but now with a much more smaller occlusion. And you see that the bicycle is driving behind the car. I mean, this is a real-world solution we probably see every day. And a lot of us have already felt or have seen or imagined that. This is something that happens basically every day. And you see again here that our car definitely slows down, but now also not slowing down and stopping the car in order to get this freezing robot problem. I mean, this is something we do not want from our car, right? That would be even worse. If you every time would just slow down and say, stop the car, if this is a too complicated scenario, it would not help anybody. So what we do here, and you see that our car slows down, moves to the right, and then accelerates at the same time. So we get quite some very smooth behavior. And that's what you see here on the left side in the graph of the velocity, that our car slows down but accelerates immediately. So we are safe but efficient at the same time. And finally, number 3, here's a result of a truck, but also with an additional house. So occlusions can not only come from obstacles that are driving on the street, they can also come from houses, for example. And you see here that this truck is standing right in the middle of the street. Again here, similar environment, similar example. You see that again here we get some good results. So finally, I just want to bring you another example. And this is something where you see that we are now in a different scenario. And this is a right turn, also a real-world scenario that you see a lot when you do this right turn. And now you see a pedestrian coming over the street. And again here, this is occluded just by the environment, okay? So we can do this calculations not only for obstacles that run on the street, you can also do that for environment behavior, right? If there is a house on the left side or on the right side and it's occluded. So you see here that all of that worked out. Of course, this is just a handful of examples, but we published that in multiple papers because what we ultimately want to do, and that's then the final result, and that just came out in a paper, and I think that's the most impressive one because that's the scenario I showed you in the beginning. So what you see now is pedestrians that walk on the street, pedestrians that are going randomly over the street, and you see our car maneuvering exactly through that environment. That was the complexity solution we are trying to solve. Imagine that as, for example, a state fair or something where in the street something is happening and an ambulance needs to rush inside, where you need to take care not of one, but like of 100 people at the same time. And you can see that with that kind of approach, we are able to calculate the occlusions now for 100 participants at the same time, predict what they are doing, accelerate the car, but slow down, especially when we see it's getting too crowded, too occluded, and therefore achieve that kind of behavior. I'm at the end of my talk. I'm also wanted to short this down because maybe you have a few questions. Therefore, just a short key takeaway. So what did you just learn from me? First of all, what you learned from me that the blind spot detection is a real thing. We need that to generalize and to solve complexity situations in the real world. In our case, we said we solving that kind of issue by combining a motion planner, by combining the motion prediction, but also with a, I would say, novel concept of creating these kind of occlusions, with these phantom objects and spaces that are free behind that. When you combine all of that together and tune it with certain parameters and KPIs, we get a nice setup that can solve the simulation and can solve the scenarios. We showed that in simulations and we showed that also in different papers, especially thanks to my PhD students, Rainer Traut and Corbinian Moller, who did all this research. And therefore, the key takeaway for you, our occlusion framework significantly enhances the autonomous driving safety and can solve these kind of situations. If you have questions, I'm looking forward to it. Otherwise, thank you very much for listening.
Dennis. All right. Great talk, very comprehensive. Now you're open for questions. If you want to have questions, you can raise your hand or go over there. Yes, please.
Hello, thank you for great talk. I would like to ask how you can, for example, behind the truck, it can be a car or it can be pedestrian or it can be bike, and our ego vehicle approach can change different objects. So how can you choose the type of the car and how you change eco vehicle?
So the first thing we always do is to take the size of the object, right? So the object is in front of us, and then we are trying to figure out what can fit behind that. In your example, let's take a truck. Behind that, everything can fit. So what we assume is worst case scenario, and starting with another car that actually comes so close to us and that we are predicting so close to us that we need to react immediately. Then, by detecting this object, when we see it, we switch to that, include the new trajectory prediction, and then can slow down responsively. What we then also do while we are driving alongside, we switch between these objects very heavily. So if we come closer and do not see this car coming out, we can also switch to other objects. So it's basically switching behind these phantom objects all the time and making that as fast as possible. That's basically the magic behind that. Yeah. And if you take then another example like a car, it's only a pedestrian or a bicycle can be behind that. And if you look at this example here very, very carefully, I think that's the one here. You see the car coming from the right side. So while this other car is driving, there's no possibility that a pedestrian is behind that anymore. It can only be a bicycle or a motorcycle because the car is moving in front of us, so we are switching to that kind of prediction. Yeah? I hope that answered your question. Thanks.
Thank you, Johannes, for the wonderful reiterated.
Oh, sorry.
Thank you for the wonderful talk, Johannes. Enjoyed it very much. I was curious in your tensor-based and cross-attention work, which things are in your embeddings? Is there shape, pose, velocity, direction?
Yeah.
What do you consider?
So it starts definitely with the shape. So a lot of the research we are doing, especially when you work with a real-world car, is building on HD maps. Without that, I'm very honest, we are a little bit lost. So we embed especially the localizations then of the different shapes of the environment. Then number two, starting with the initial position and the heading. That's also very important for us to actually start with that kind of predictions. That's the two main things we need here. Velocity comes then in number three, but I would say the map environment, the lanes, then the position, this was the most important part. Yeah, you're welcome. Thanks for the question.